Hello and welcome, class. We have just concluded our lecture series for Chapter 16, Introducing Equilibrium. Today we are going to be applying what we have learned about equilibrium to an old lesson, one that goes back all the way to Chapter 9, that of solubility. So you may notice on the slide it does say we are jumping to Chapter 18. That is true. We are putting a pin in Chapter 17. The main reason being is that the topic of solubility in the textbook always seems to be, or at least in our textbook, seems to be presented generally as an afterthought, but I find it to be a really nice smooth transition from the basis of equilibrium to some of the more complicated types of chemical reactions we can look at. So we are going to be, today, turning our attention to the mostly insoluble compounds from back in Chapter 9 and using equilibrium and reversible reactions to really understand what this mostly insoluble means. Okay, so let's talk a little bit about solubility. We're going to shine a new light on solubility as well, a little bit more technical. Our conversation of solubility last semester primarily had to do with the qualitative description of solutes existing inside of solvents, and we did talk about the nature of solubility this semester, that with an increase in temperature, generally we see an increase in solubility of the solute particles hanging out inside of your solution. So the concept of solubility and how it connects explicitly to the definition of a saturated solution. We can measure the solubility quantifiably of a solution, and this is the maximum amount of your solute that can dissolve in a given quantity of solvent at a specific temperature. Now, this is going to be measured in grams per liter. So in other words, once we have a saturated solution, we have as much solute as we can fit. The spheres of hydration cannot accommodate any more solute going into the solution. We're going to have a certain mass of stuff inside of this given volume of solvent. And so the solubility of a saturated solution we can actually measure, because one more particle of solute being added into this container would just sink to the bottom. There's no way for water to accommodate it. It's not going to form a solution. It's going to remain separate, this little heterogeneous piece of leftover solute at the bottom. So the amount of stuff that's in solution defines our solubility. Now we can also rewrite our solubility known as our molar solubility with the shorthand of this lowercase s, this variable s. This is the number of moles dissolved in 1 liter of a saturated solution. So notice that solubility, the molar solubility, is defined similarly to the same type of concentration, molarity before. So we have moles of a solute in some volume, specifically that's in liters of a saturated solution. So we're still looking at liters of solution here. Okay, so we can use the molar mass, grams per mole, to convert between the two of these. So the solubility in grams per liter can be interchanged with the molar solubility that is in moles per liter, here using grams per mole. Okay, so let's tie in then those mostly insoluble compounds. Solubility rules, again, that I've posted on Blackboard as a refresher, can be used to determine whether an ionic compound is mostly soluble or mostly insoluble. But what does that really mean? We're going to be focusing on the mostly insoluble, but the same types of arguments can be made for mostly soluble compounds, and we'll talk about that a little bit later. The mostly insoluble ionic compounds, when the solid itself is placed in solution, we can say are going to slightly and reversibly dissolve in aqueous solution. In other words, these types of compounds like this lead iodide, which we would predict using our solubility rules to be a mostly insoluble compound, so this is an example of a mostly insoluble compound, we would predict this to just sit in solution. It would be mostly insoluble. But mostly insoluble, meaning that most of the time these ions are recombining to form a solid. Some of the time, though, we have a little bit of dissociation, right? So these forward and reverse reaction arrows, tying them back to the idea of rates from before. Here we would have a very fast rate going backwards, very high reaction rate going from the ions into this solid, but a very tiny right? A little tiny reaction rate going from the solid into the ions. This reaction will eventually hit some type of equilibrium, giving us an equilibrium constant that we can write out. So in fact, let's do that. What is the equilibrium expression for a mostly insoluble ionic compound? Since this way of writing the formula is going to be kind of the common thread. This is the, by convention, standard way that we write a mostly insoluble solid partially dissolving into ions in solution. So we're, again, going to be writing our equilibrium expression as an expression of products over reactants. This does not change, right? Just because we have slightly altered the focus of our equilibrium study doesn't mean that we throw everything out the window. We are still going to be writing a ratio of product concentration divided by reactant concentration. It just so happens in this case that the mostly insoluble kind of like concept that we're working with, we are working with heterogeneous equilibria, right? We have aqueous species on the right-hand side and solid on the left-hand side. And when it comes to the heterogeneous equilibrium expressions, as a reminder, we do not include solid or liquid in our equilibrium expressions. What this means is that the equilibrium expression is only going to be equal to the concentration of our lead 2+ ion times the concentration of our iodide ion, and because we have a coefficient of 2 in front of the iodide, we're going to square it. So this is going to be what the equilibrium expression looks like for a mostly insoluble compound. It's almost always, like 99 times out of 100, going to be equal to the concentration of the ions that are the product of the dissolution, and the solid itself, it doesn't matter. And again, we don't include the solids or the liquids, but in this section we're going to be seeing solids mostly. The reason we don't include those solids is specifically because, again, the densities don't change. So even if we included something like density of lead iodide down here, across the board with all of our different calculations, different temperatures, etc., this density doesn't change. And so if it doesn't change, it's not going to alter this measurement of K or the idea of these concentrations in any way. So if it's just a constant, we might as well drop it. If we're looking at ratios, it doesn't give us any additional information. So we're just going to be focusing on the aqueous components here. Okay, so what does the magnitude then of this equilibrium expression mean? Well, before talking about that, let's introduce then the new notation for this specific type of Kc. And this is, the C now we can see is going to be changed in this context to an SP. We call this our solubility product. This is the equilibrium constant expressing the product of solubility. So in other words, the Kc that we just found on the previous slide, if we are working with mostly insoluble species, we are going to rewrite this K as a Ksp. There's no like conversion that we have to do. It's just a simple label change. We are changing the subscript to an Sp to specify that we are working with some type of heterogeneous, mostly insoluble type of equilibria. So we see two additional examples of this type of solubility equilibria below. We have strontium sulfate, which we would predict to be mostly insoluble. Now this bismuth sulfide was not necessarily on the list. I mean, sulfides were, we could assume that this is mostly insoluble, but just because both of these compounds we would label before as mostly insoluble doesn't mean that they are mostly insoluble to the same degree. In fact, the strontium sulfate, which breaks into our strontium and our sulfate, we see has a Ksp that is equal to 3.8 times 10 to the negative 7. We're going to look at these magnitudes for comparison's sake. The bismuth sulfide, which breaks into bismuth and sulfide, as one would expect, has a Ksp that is 1.6 times 10 to the negative 72. This is a huge magnitude difference. And what this really means is that, again, if we're looking at these Ksps being a measure of like product over reactant, where yes, the reactant we're not explicitly going to list, but we're still going to look at this Ksp conceptually as this like meaning of product to ratio or product to reactant ratio. The first Ksp for strontium sulfate is bigger. What this means is that we have more product, right? A larger Ksp means more relative product. And in this case, the product that we're looking at in both cases are ions that have been dissolved in solution. So a larger Ksp is also going to mean that your quote-unquote mostly insoluble solid is more soluble. We can dissolve more strontium sulfate in water than what we can bismuth sulfide. In fact, this magnitude, this negative 72, or the 1.6 times 10 to the negative 72, is so incredibly small, we would have like one ion in solution. Like one of the molecules would break apart, but we would have this very heavy reverse equilibrium balance where most of the bismuth sulfide is just going to remain as solid. And that's not to say that 10 to the negative 7 isn't also a small number, relatively speaking, to other numbers that we've been looking at for equilibrium constants, but this is to say that it is a larger Ksp, meaning that more of the strontium sulfate will be able to dissolve. Okay, so where can we find tables of these Ksp values? Since the solids that we're looking at are mostly insoluble solids, this is not, an indefinite list of solids that we could be looking at. So we actually have a couple of places where we can go find already like predetermined Ksp values. So in table 17.4 in the text, as well as appendix 3, we have a bunch of solubilities. That's actually where I grabbed these two solubilities from. So if you're working on homework problems and a Ksp is not given to you, feel free, to check out these tables here and pick out the Ksp that you are going to presumably be working with. Okay. 3. Yes. 3, 2. Wait. Okay. 3, 2. All right, now that we have the solubility product, this Ksp, how does it, though, quantifiably relate back to our solubility that we were talking about? I mean, I did just say that solubility and Ksp are somewhat proportional to each other, but we can actually find a quantifiable measurement for solubility based off of our Ksp if we know it. So that's what we're going to be talking about here, just the general setup for how we can approach these types of Ksp problems. Then we're going to look at a couple of examples for how we can use Ksp to explicitly find solubility, as well as solubility to find Ksp. All right, so we can use our ice tables method, like how we have learned in chapter 16. So we can see that's exactly what I've laid out here. We have lead iodide as a solid breaking down reversibly to create lead ion with a 2+ charge and 2 iodide ions with a minus charge. Notice that I have this big red X underneath the lead iodide. I would advise getting into this habit when working with Ksp. Just put a huge X underneath your solid compound because, again, solids don't get included in our equilibrium expressions. So it's actually a really nice reminder, like we don't have to worry about initial measurements or concentrations or densities when it comes to the solid in these Ksp problems. We only have to pay attention to the ions, like here, the lead and the iodide, that the solid dissolves into. All right, so let's say hypothetically we take a chunk of lead iodide and throw it in some water. This water did not have any lead or iodide initially in it, hence the 0 molar present in the initial row. We can see right here, I for initial. So there's 0 lead to start with, 0 iodide to start with. As we have seen now a couple of times with our equilibrium expression problems, anytime you have nothing on one side of your reaction to start, your reaction is going to have to shift in that direction during the change phase, or changing stage, I guess. So the change we would normally write as a plus x and a plus 2x. Here we can see, though, the notation in this ice table is a little bit different. Instead of an x, we have written an s. So we are not just looking at a plus x or a plus 2x, we are looking at a plus s and a plus 2s. Why do we do this? Well, the reason why is solubility, specifically in units of molarity, is defined by this variable s. So the same x that we've been working with in our previous tables is now going to change variable. Conceptually, we still work with it the same way. It's still the unknown variable inside of our ice tables. It just has a change of appearance, right? It's putting on a different outfit for the day. So in order to use Ksp to find molar solubility, all we need to do then is acknowledge that at equilibrium, again, assuming we didn't have any of these ions in solution to start with, we will now have S molarity for our lead 2+, and 2s molarity for our iodide. And again, this 2 is coming from the fact that our iodide has a stoichiometric coefficient of 2 in front of it. So initially, there was nothing. Change, we would expect to see an addition of our product, and at equilibrium, we would have proportionally s or x in the old variable terms for our lead, and 2s or 2x for our iodide in terms of like its new concentration. All right, so how we use this then to find molar solubility is in the really straightforward equilibrium expression, just like how we found x in the past. So our Ksp expression, we can see here, Ksp again standing for solubility product, is equal to the concentration of lead 2+ times concentration of iodide squared. Again, products divided by reactants, except we don't care about the reactant in the equilibrium expression in this case. And we're going to take our equilibrium concentrations with this variable of s and just plug them straight in. So our concentration of lead would be s, concentration of iodide would be 2s, and we're going to square that variable. All right, so we can combine variables now, just as we have learned many times in algebra. If you're taking like x times x, that becomes x squared. In this case, we're taking s times 2s squared. So we're going to simplify this square first. We're going to distribute this. This becomes s times 4s squared. And if we simplify this again, our Ksp is going to be equal to 4s cubed. Now, what this means is if we know what our Ksp is, which we can go back to, again, Appendix 18.4 or Appendix 3 in order to find a Ksp value, all we need to do is rearrange and solve for this variable s to know exactly what the molar solubility in molarity, again, in moles per liter, for this lead iodide would be. All right, so let's look at a couple of example problems. Again, one in which we go through this process for a different compound, setting up our ice table from the start. I'm going to let you guys kind of work through that now that you can see in general what we're going to be looking for. And similarly, we're going to start with solubility and then find our Ksp. We can calculate the solubility S, so this is again our molar solubility S, that we're first going to be finding for magnesium carbonate. This is another substance that we would predict to be mostly insoluble. Ksp is provided here, a 6.8 times 10 to the negative 6. So this is on the same magnitude as the strontium sulfate that we just looked at. Now this is a component inside of the mineral dolomite. Let's also then, once we have the molar solubility, just for the sake of practice, find the basic solubility in grams per liter. Let's see if we can't find the value in both of these units. Okay, so the way that we set up this problem is the exact same way that we have been setting up any type of equilibrium constants type of problem. So we're going to set up first our reversible reaction, the magnesium carbonate, which is a solid. This is going to dissolve reversibly in water, giving us magnesium 2+ and CO3 2-. Both of these will be aqueous. All right, once we have the dissolution written out, it's just a matter of entering data that we either have or don't have in some type of ice table. And this may seem a little strange since we're not given any information aside from the Ksp of the magnesium carbonate, but here is sort of the implied direction that we're going to be starting from. First, Our magnesium carbonate, again, since this is a solid and this species does not get included in our equilibrium constant, we're not going to fill out any information here. It doesn't matter. It doesn't matter how much we start with. If we add too much or too little, the question is, what is the solubility? How much solute would theoretically be able to fit inside of a given volume of solvent? So it doesn't matter how much we're starting with, we're looking at a hypothetical theoretical limit. What is the amount we could add to a saturated solution? All right, well, you might then ask, how can we find that if if it doesn't even matter how much magnesium carbonate we're starting with? Well, here's how we can find it. The Ksp tells us the threshold limit, how much stuff can fit inside of solution when our stuff is magnesium carbonate. So if we throw in some amount of magnesium carbonate, doesn't matter how much, initially, we would assume that we're starting, right, with just pure water. We're taking magnesium carbonate and we're throwing it into some container that is just pure water. And if this is our initial condition, we're taking some stuff and throwing it in pure water, well, that means that we don't have any magnesium or carbonate to start with. Now, in order for this reaction from these initial conditions to change and reach equilibrium, there's going to have to be some type of shift from the magnesium carbonate as it partially dissolves into the magnesium and carbonate ions. This shift we're going to represent with an S. So from here we have the magnesium carbonate dissolving into some amount of magnesium and carbonate being represented by this S. And so once we've reached equilibrium, the amount that we're going to have is going to exactly be equal to S. So now we have one unknown and one equation that we can set up using this Ksp. All right, so I've erased some of the writing from over here. Do not be alarmed, quick cut, just erase that material so I have room to work and write out what that Ksp expression is going to be equal to. So again, products divided by reactants, but it's only the product that is going to matter here since these species are in aqueous form. The Ksp is going to be equal to the concentration of our magnesium 2+ times the concentration of our CO3 2-. No exponents necessary since there are no stoichiometric coefficients here, so it's just a matter now of inserting what our Ksp is equal to, the 6.8 times 10 to the negative 6, and this is going to be equal to S, which is the concentration of our magnesium, and S, the concentration of our carbonate. Well, this is just equal to S squared. And the easiest way to solve for a square is to take the square root. And so this is going to give us what our S is equal to, at least in the units of moles per liter. Again, this table here, all of the variables within it, in order to work with Ksp, are going to be in mole per liter units. Has to be. So it doesn't matter that our Ksp does not carry any units explicitly with it, so long as we remember that this Ksp is a molar equilibrium, then we will remember that the S's that we calculate on the other end, which in this case the square root of 6.8 times 10 to the negative 6, is a 0.0026, the units will be molar. All right, so here's the first value that we were asked to find. The molar solubility S is going to be some type of mole per liter unit. Now let's find what this value is in grams per liter. The easiest conversion that we have to do is just take this, multiply it by our molar mass. So the 0.0026 mole per liter, we're going to take this and multiply it by the molar mass of magnesium carbonate, which is an 84.31 grams per mole. So here now we can see our units of moles are going to cancel, and this will leave us in a unit that is grams per liter. And our grams per liter are going to be a 0.22 measure for solubility. All right, so what all of this means is that we can take either 0.0026 moles of magnesium carbonate, or in a more conceptual measurement for us, a more direct measurement, 0.22 grams per liter, or grams of magnesium carbonate, and this would dissolve in 1 liter of solvent. We would have no precipitate, it would be completely dissolved, we would have a saturated solution. Any more than that 0.22 grams would just sit at the bottom of our beaker, sort of like sand or glass or any type of solid that we would put in a flask of water that does not dissolve. It would just sit there. All right, so that was finding our solubility from Ksp. Here what we're going to do is find Ksp from solubility. So we're told that the molar solubility for copper sulfate is 1.26 molarity at 20 degrees Celsius. So I would like you guys to try your hand then at using this information in order to calculate the Ksp of copper sulfate. All right, so welcome back. Hopefully you took the time to approach this problem. Where are we going to start? In the place that we always start when we are working with chemical reactions. We are going to start by writing out our chemical equation. So the equation, again, is super useful. It tells us what variables in terms of the chemicals we're actually working with. So copper sulfate, CuSO4, which is a solid, we would predict is going to break down into the following ions reversibly in solution. Copper with a 2+ charge in aqueous phase, and this 2+ charge comes from the fact that we know that sulfate has a 2- charge. So again, if you're a little bit rusty with your polyatomic ions, this would be a great time to brush off those old skills, those old lessons. So since we can see in the chemical formula, copper and sulfate exist in a 1-to-1. We know, again, sulfate has a 2- charge. Therefore, this copper must have a 2+ charge. All right, so we're also going to assume, regardless as to what the old solubility rules said, we will assume here, as we will for the rest of chapter 18, that all of our solids will dissolve reversibly, no matter how soluble they are. So we're going to now write our I, C, and E here. And if you're really good at recognizing patterns, I will say that there's kind of a point where you don't have to necessarily write out the entirety of the ICE table. If you're at that point already, cool beans. If not, there is no shame in always writing out your work. I still, to this day, write out all of my work, still using ICE tables. It's just so hard for me to keep track of numbers in my head. All right, so we take some copper sulfate, we throw it in water. We're assuming initially, just like how we did with the previous examples, there was no copper and no sulfate in the water to start with. There must be a shift in conditions in order for this equation to reach equilibrium. So we would expect that there's going to be some copper and some sulfate that does dissolve proportionally to this variable of S. Now, because there are only stoichiometric coefficients of 1s in front of the copper and the sulfate, we're not going to have to add any coefficients down here. It's just 1s proportionally for both. Meaning at equilibrium, we should have concentrations of S for both the copper and the sulfate. All right, so our equilibrium constant, which we do not know what its value is going to have to be equal to the concentration of copper 2+ times the concentration of SO4 2-, and this will be equal then to S squared. All right, well, this is fine. It seems like we now have one equation and two unknowns, except if we return to the wording of our problem, we're told that the molar solubility of copper sulfate is 1.26 molar. This means we can just plug in the 1.26 molar right here and square the value. Again, molar solubility is synonymous with the variable S. So we don't have to worry about splitting this 1.26 between the copper and the sulfate separately. Each variable of S gets a 1.26 plugged in for it. So this tells us that our Ksp must be equal to 1.26 squared, which is equal then to 1.59. Now 1.59 is proportionally, if we're thinking back to the ranges of all of our Ks, definitely in that middle ground. It's less than 1,000, but it's greater than 1,000th. So what this tells us is that copper sulfate is intermittently soluble. It is going to be reversibly soluble, which means that according to temperature and Le Chatelier's and all of the previous things we've talked about, we can actually push our reaction in one direction or the other. It's going to be very easy for us to manipulate since it is in that sweet spot for being a great reversible reaction. Okay, so let's talk about how the idea of solubility then connects to precipitation reactions. Now, we did this last semester as well. We predicted based on some type of cation plus some type of anion, if they combine together to make Ca, was Ca soluble? We would look at this compound try to find it somewhere on, the solubility rule list, and we would determine, is it mostly soluble or mostly insoluble? Well, here we can do the same thing quantifiably. So we don't have to have a bunch of rules memorized for a bunch of different compounds. If we know what our Ksp is, and we know what our initial conditions are, this Q is the exact same reaction quotient from chapter 15. So if we know our initial conditions and we can compare them to equilibrium conditions, we can, predict whether or not a precipitate is actually going to form. So if we take some type of cation like lead, mix it with iodine to create lead iodide. Now this is the compound that we're going to say, okay, if it is mostly insoluble or not, it in solution will start as some type of solid and will then react reversibly to dissolve. Now we can set this up whether or not we know our compound is going to be mostly soluble or insoluble. The process is going to look the exact same. We have a Kc given here. Now, if our initial conditions compared to this K, so we know how much stuff, how many of our lead and iodide, molecules that we're putting into solution because we have some type of concentration measured. Again, if we write the reaction in the forwards or reverse direction, it doesn't matter, just so long as we are looking at the problem consistently. And so this is going to be the consistent perspective that we are going to take, since we have an equilibrium constant here that we can actually compare initial conditions to. If we know the initial concentration of our lead and our iodide, we can compare the initial conditions to Kc by taking the initial conditions, Q, and inserting them to find a reaction quotient. Right, so here's our Pb2 plus initially, and our iodide squared initially. So if this calculation for Q, when compared to K, Q is less than K, well, what this means is that in order for Q to be smaller than K, if we're looking at this versus this, let's compare the right-hand side since this is where useful information is. What this means is that the value of our lead concentration and iodide concentration, our products, in other words, are too small, right? We have too little of our product compared to our equilibrium conditions. Well, what this means, if our products are too small, it means that we don't have enough ions. Not enough ions. We have not made a saturated solution yet. What this tells us, if we have not made a saturated solution, is that more ions can still fit inside of solution. In other words, if our Q is less than our K, no precipitate will form. Right? And no precipitate will form because we don't have enough ions in solution yet. We have not reached a saturation point. Now, if Q is greater than K, this is going to mean the exact opposite. If Q is too big, that means that our initial conditions, there are too many ions. Our products are too big. Mathematically speaking, we have too much stuff in solution. Too much stuff. There are too many ions. Not everything can fit. So if your Q is greater than K, if your reaction quotient is greater than your equilibrium constant, then a precipitate will form. The reaction will have to shift away from the products, and if it does that, it's going to shift towards the reactant, which in this case is a solid lead iodide, meaning that we would see some type of precipitate form. So let's look at some hypothetical numbers then. Let's actually plug some numbers into the equilibrium reaction, reversible reaction. My brain just farted there. A reversible reaction of our lead iodide, solid, not gas, dissolving reversibly with lead 2+, an aqueous condition, and our 2 iodides aqueous condition. So we just saw, and as we have also written already, our Kc, which is going to be equal to the concentration of our lead 2 plus times our iodine concentration squared. Now in the wording of this problem that I have yet to read out loud, we can see is equal to numerically a 1.4 times 10 to the negative 8. So this is going to be the value that we are going to compare our Q to. Now what we are mixing together is a 4.3 times 10 to the negative third molar solution of lead nitrate. So this is going to give us our lead concentration here. And it is mixed with a 7.8 times 10 to the negative 4 molar solution of sodium iodide. This is going to give us our iodine concentration here. The question is, will a precipitate form? All right, so how we can solve this problem is set up our Q, and we're going to compare our Q to our K that is now listed to the left. Our Kc, again, which is some type of solubility product. We could also write this as a Ksp. It doesn't matter. Both of them are the same variable. There's no mathematic calculation we need to do to interchange between the two. It's just a simple label change. So the Q is going to be equal to our concentration of lead 2 plus times the concentration of our iodine squared. So we're going to take the concentration of our lead, which is given to us up above, a 4.3 times 10 to the negative third molar. The concentration of our iodine is 7.8 times 10 to the negative 4 molar, and we're going to square that value. And this is going to give us a reaction quotient that gives us information about the initial conditions relative to our equilibrium expression and our equilibrium constant. So the calculation of 4.3 times 10 to the negative third and 7.8 times 10 to the negative 4 squared gives us a 2.62 times 10 to the negative 9. Now this reaction quotient Q is going to tell us whether or not we're going to get some type of precipitate, and we're going to compare this Q to our K here. So our question is Q less than K or is Q greater than K? Now in this case, we can see that a 2.62 times 10 to the negative 9, this is one full magnitude smaller than our K. Our Q is less than our K. And since our Q, our reaction quotient, is smaller than our K, what this means is that we don't have enough ions in solution to have reached a saturation point. We are going to need more ions to reach saturation. Given the concentrations that we have mixed together, we would not see a precipitate form. There's not enough lead and iodine in solution to cause the reaction to shift to the left to create any type of lead iodide. There would be no solid. We would see two solutions that are clear and colorless being mixed together that would also result in a clear and colorless solution. Now, this may seem counterintuitive. Again, based on our solubility rules, we predict that if lead and iodide get mixed together, we would see some type of precipitate form because lead iodide is a mostly insoluble compound. However, what we're doing now is that we're actually looking at, again, the gray area. What happens when you don't have enough ions in solution to actually cause some type of solid to form? This is exactly what's going to happen. The calculation that we've just done demonstrates or links together the idea of solubility in saturated solutions with equilibrium. And now we have a means to predict every time, not just based on general rules, but every time whether or not we will see some type of precipitate form. Okay, so notice that we didn't have to do any complicated ice table here. We didn't have to find any type of equilibrium calculation or concentration. Didn't have to go that far. If we're looking at whether or not a precipitate forms, all it is a simple measure of Q versus K. So if you can find your Q and you already have a K, or vice versa, if you have a Q, but you're trying to find a K, but you have equilibrium concentrations, or you can look it up in the tables provided, you have a way to figure out whether or not a precipitate will form without any additional calculation. Now, these conversations so far of solubility, just of a compound being dumped into water on its own, or solubility pertaining to like when we're mixing two different substances together and testing for precipitate formation, all again come down to whether or not we are observing an unsaturated unsaturated solution versus a saturated solution. So this is a simple reminder, a harken back to chapter 13 when we were studying solutions and solution properties, that an unsaturated solution is always possible so long as the saturation point is not reached. This is like back in, again, the chapter 9, chapter 13 era, really simple to understand if we're thinking of just purely a substance being soluble and we eventually reach some kind of saturation limit. But it's true as well for when we are working with mostly insoluble compounds. Each compound, if it can be added into water, will dissolve to some capacity. It's just, what is that capacity? Some substances like sodium chloride have incredibly high KSPs, meaning you can dissolve a whole bunch of it before you reach that limit. Some substances like our lead iodide that we just looked at an example for have a much smaller limit. Their KSPs are very, very small. Once we have added enough of our reactant into, or our two different reactants into our solution, such that Q is equal to K, we now have reached a point where we are at that saturation limit. Anytime our Q is greater than our K, that must mean that there's going to be a little bit of solid sitting inside of our solution, because we have too many products according to our reactions, the way that we have them written, meaning that a solid must form. So if our Q is equal to K, we are saturated, perfectly saturated, no excess, but once that Q is greater than our K, we are going to go beyond that saturation limit. Now, if we're working with something like a supersaturated solution, we increase the temperature, let's say, sure, we can increase the solubility, we can get more stuff, more solute to fit into the gaps between all of our solvent particles, but conventionally, supersaturated solutions are hard to come by, they're hard to work with, they're very finicky, and so what you're oftentimes going to see instead of a supersaturated solution is just a pile of precipitate sitting at the bottom of your beaker. All right, so we just looked at an example problem of, we mixed two solutions together, we mixed two substances together, we checked to see whether or not a precipitate would form. But let's take this idea of unsaturated versus saturated and push it one step further. If we're observing precipitation reactions and we know we're mixing two things together that could hypothetically create some type of precipitate, we now also have the means to determine what's the maximum amount of two reactants we can mix together without causing a precipitate to form. So for example here, we're looking at what is the maximum amount of sodium chloride that can be added, specifically if we're looking in grams, to 1 liters of a 4.5 times 10 to the negative 6 molar silver nitrate solution. And specifically, we're looking to add enough sodium chloride, just enough such that we do not cause a precipitate. All right, we're also told in this problem what the KSP of silver chloride is. So I would like you guys to kind of take a breather, absorb everything we have been talking about from solubility to precipitation, and see if you can't figure out how much sodium chloride you can add on your own, and then we'll double check our work together. All right, so we're mixing two things together. We're also given a KSP. This KSP is super useful to us because it tells us which of the ions in our reactants, like which ones will come together to form some precipitate. Now we could always go back and use our solubility rules from chapter 9. They are very useful in terms of like being a launching point if you're not sure what cation and anion could come together to make a precipitate, but you can also look somewhere else in the problem, like in this case with our KSP, to get an idea for like which things are going to be coming together to give us something that would be hypothetically insoluble. All right, so we're told AgCl is going to be our precipitate here. AgCl, let's see, and I'll write it over here. AgCl is going to be a solid, and again, we're hoping our aim is to not actually make this solid, but in order to use Q and K and all of our equilibrium calculations, we do need to assume that there is going to be a possible reversible reaction that could occur. The silver chloride will break down into silver in aqueous form and chloride also in aqueous form. And we don't need to go through the whole process of writing an ice table. In this case, we're not looking for equilibrium necessarily. We're looking for change. In which direction will this equation shift? In other words, how much can we add of one reactant without causing a significant shift? That's a better way to put what we're looking for. All right, so we're told some initial amounts here. We are told, for instance, that the silver solution has a concentration of 4.5 times 10 to the negative 6 molar. And we are not told, again, how much of the chloride we have, since the silver chloride here is our variable, it's our question mark. We do, however, know what our Ksp is. Ksp is equal to 1.6 times 10 to the negative 10. And in order to solve this problem, we want to make sure that our Q, let's see, I'll write it here, which is equal to the multiple of our concentrations for silver and chloride, we want this value to be less than our Ksp. Again, if our Q is less than our Ksp, it means that we proportionally do not have enough product, and that's going to make sure that the reaction, this reversible reaction we're working with, will still be moving predominantly in this forwards direction. This is what we want. Again, we're not trying to cause a precipitate. In fact, we're actively trying to not cause a precipitate. So we want to make sure that the forward direction of this reaction is going to be dominant to make sure that silver and chloride remain dissolved. Okay, well, we know again what our concentration of the silver ion is in solution. We don't know this chloride, and that's perfectly fine at this stage. Our silver is 4.5 times 10 to the negative 6 molar. Chloride is an unknown, and we want this value, this multiple, to be less than 1.6 times 10 to the negative, 10, 1, 0. All right, so here now we can see that we do have one variable and one equation, one unknown, this unknown variable being what is the concentration of Cl minus at this point, like what is the highest that this Cl minus can be while still allowing this product here, this multiple, to be less than our Ksp value. Well, in order to find this, all we need to do is divide the 4.5 times 10 to the negative 6 over to the right-hand side. So we know that our concentration of Cl minus must remain less than 3.55 times 10 to the negative 5 molar. Right? This makes sense. We want to make sure that, again, the product of these two ions is going to be small enough such that our forward reaction is still going to be dominant. So hypothetically, if the concentration of our Cl minus here is less than 3.55 times 10 to the negative 5 molar, we should still see a forward dominant reaction. All right, but that's not necessarily what the question was asking for, right? It wasn't asking for what's the maximum concentration of chloride. It was asking for how much chloride. Like, how much could I measure in the lab and sprinkle into this solution and still not see a precipitate form? Well, this calculation, this final step, is something that we've been doing for nearly a year now, right? If I told you or gave you a concentration, which I did here, 3.55 times 10 to the negative 5, and gave you a volume, which you can see here, we're working with a 1 liter solution, and asked you what mass of sodium chloride was necessary to make this solution, you would be able to calculate it using dimensional analysis and your molar mass. So that's exactly what we can do here in our final step. 1 liter multiplied by 3.55 times 10 to the negative 5 moles in every single 1 liter. And then if we want to get out of the unit of the mole and into the unit of the gram, we must use the molar mass of our sodium chloride. Now I am making a little bit of a jump in logic here, so just to like scale it back a little bit, this concentration of 3.55 times 10 to the negative 5 molar does pertain to chloride ion, not sodium chloride, but because these two things, like chloride comes out of sodium chloride in a 1-to-1 ratio, in other words, 1 mole of Cl minus per every 1 mole of NaCl. 1 divided by 1 here, or 1 multiplied by any number is going to end up kind of canceling out. So just to explicitly include it in the writing here, that's fine. There will be some problems where there is this proportion is not going to be a 1-to-1, so definitely watch out for it. But at this point in the semester, it's sort of one of those like leaps of logic that we can make just because we've seen it 100 times. All right, the last thing we have to multiply then is by our molar mass. 58.44 grams per every 1 mole of sodium chloride. And this tells us that the maximum amount in grams of the sodium chloride we can sprinkle into the solution and not see a precipitate is going to be 0.00208 grams. So 2/1000ths of a gram. This is a very, very, very tiny amount of salt. But suffice to say that if we took this very, very tiny amount of salt and sprinkled it into this particular silver nitrate solution, we would not see a precipitate. We would be on the cusp of a saturated solution if we measured exactly 0.00208 and added it to solution. We would be at that saturation point. Even 1 grain more of sodium chloride would tip the scales and cause a precipitate of the silver chloride to start to form. And that is going to conclude our lecture for the day. So here we can see some example problems that can be found on page 876. We have made it through 800 pages of our textbook, like nearly 900 pages so far this semester, which is pretty awesome. So yeah, here we have a few example problems pertaining to Ksp and precipitation. Being able to study and observe these solubility and precipitation-based problems, from the reversible reaction perspective. So as always, though, if you have any questions, please do not hesitate to let me know. If you have any homework, double check and do your homework. And until next time, class is dismissed.